I'm from Marshall Space Flight Center. I run our partnerships office, and I've been doing that for about 3 or 4 years now. And it's really kind of neat to see what has happened in the industry, what has happened, and how we're trying to grow. And so my talk today, rockets, sales, and Stardust. So it's a little bit of everything that we do at Marshall, and just kind of giving a synopsis and giving our perspective, our view of what we're trying to do and where we're trying to go, and how we're trying to leverage the relationships that we have with companies and the ability that we can grow from that. So we recently got a new center director, Jody Singer. She came in, she announced her 3 themes for our center. And it's focused on mission, getting the job done, our people, growing our people and developing our people, and partnerships. So we're not going to do it alone. And so I thought that was pretty telling, and it's pretty beneficial to our office in making sure that we do our role and our responsibility to get the partnerships in place. So exploration is what we're trying to do. Exploration is inherent. It's in us, and it's been in you since you were a little kid. And if you want proof, go to the beach. That is the best place to find where exploration begins. Because you walk along the beach there at Cocoa Beach, if you're at Kennedy Space Center or anything of that nature, and inevitably, almost every single family, at some point in time during the day, those kids are digging a hole in the sand. And why are they digging a hole in the sand? You ask any one of them, whoever knows, just to see. Buried treasure. Buried treasure. Are they going to find buried treasure? No, they're not going to find buried treasure, but they're exploring. They're finding it. It's down there, and they're going to dig it up, man. They're just looking, or they're just digging a hole just to dig a hole. Why'd you climb that mountain? Just to climb it. I'm an explorer. Why'd we go to the moon? Because we want to discover more about where we haven't been. I haven't been beneath the sand. I'm digging a hole. It's innate. It's in us. We want to do it. But then we grow up. And then what? Well, big kids explore space. And that's a pretty cool environment to go exploring in. So the whole idea about exploring space and getting out there, you've got self-funded entrepreneurs, obviously, with a lot of the companies out there, with Elon and Jeff. You've got people that are going out and scrapping together funds to be able to do their exploration. A lot of our entrepreneurs, that's great too. But the matter of getting to space, how do you get to space? That's a core crux, a core capability of Marshall Space Flight Center in Huntsville, Alabama. We have the history of the Saturn V rocket with Werner von Braun designing it, building it, testing it there at Marshall Space Flight Center. The ground shook pretty good back in the 60s. We're still doing rockets. We're still developing systems. We have the space launch system that we're developing. But it's all about getting to space, and it's the propulsion systems that get us there that we're focused on. So when you think about it, getting to space, it's not that difficult. Balloons, they fly at maximum altitude of about 25 miles. Okay, cool. Satellites fly at a minimum altitude of about 75 miles. Okay, cool. What about those 50 miles between, the 25 to 75 miles? So you've got, let's see, the stratosphere goes from 20 kilometers to 50 kilometers. So balloons go 40 kilometers, satellites down to 120. So between 20 and 50 is the stratosphere. You got 50 to 80 kilometers in mesosphere, and then 85 to 120 kilometers is the lower thermosphere. So all of that aspect, where between the balloons and the satellites, the ignorosphere, right? So we don't get much data out of that. And we obviously would like to know more about what's going on in that area where northern lights are developed. All of the plasma gases and interactions there. We want to understand that better. How do you get that? So you do sounding rockets. So sounding rockets, suborbital rockets, they range anywhere from 20 feet to 35 feet tall, anywhere from 1.5 feet to 2 feet in diameter. And so those of you that aren't familiar with sounding rockets, they can fly up to anywhere from, we're looking at 31 miles to 932 miles into the atmosphere, straight up and straight down. So that's pretty high, obviously. But how high is high? So for those that aren't familiar, the space station flies at, anybody guess? Right, so right around 200 miles an hour, 200 miles. So what did we say sounding rockets go to? 932 miles. So they are going way past the space station and then coming back down. Why are they so big? And the aspect is, going up and down is easy. You want to get into orbital velocity? That takes a whole lot of more energy because you got to start going horizontal. And it's all the premise of Newton's cannon. So if you take a softball and I hand it to this gentleman in the front row and tell him to throw it, he throws it and it goes and it hits the ground. So we go, that's nice, thank you very much. We go to another gentleman, can you throw it a little harder, please? And it throws it harder, it goes further, but it still hits the ground. So then we pull out the bowl of Magic Lucky Charms. We get my friend Rose over here. She eats the bowl of Magic Lucky Charms. I give her the ball. She throws the ball. Now when she throws it 200 miles up, 150 miles up, and she throws it 17,500 miles an hour that way. That's the clincher. The 200 miles up is easy. We can do that with sounding rockets. The 17,500 miles per hour that way, so as you're flying and the Earth is curving away and gravity is pulling you down, but you're going so fast that you keep missing the Earth. And that's the fundamentals of getting into orbit. You got to go 17,500 miles per hour at a right altitude to keep orbiting the Earth. Gravity keeps pulling you in, but you keep going so fast that you never fall and hit the ground because the Earth curves away. So that's why you take such a huge rocket to get that 17,500 miles per hour in the horizontal direction. That's what we're focused on. That's what we're trying to grow. Those are the capabilities we're trying to create. The ability to do that and grow that and make that opportunity available for small companies and large companies to go off and explore that area, that's what we're partnering for. And so there's a lot of growth, there's a lot of development of technology, there's a lot of advanced manufacturing that's being used, additive manufacturing in the building of our rocket engines that we're working with companies to develop. And it comes, bits and pieces. So Saturn V was a pretty large rocket, 363 feet tall. It could carry 310,000 pounds to low Earth orbit, or it could take 107,000 pounds to the moon, and had a thrust of 7.8 million pounds of thrust. So that's pretty much our benchmark. People aren't really surpassing that right now with our new technologies, but then again, even getting to the moon, we have different focuses right now. We're stepping up to what we're going to try to do, and as well as make it to the lunar and beyond. So we work on that. Now, Falcon Heavy's coming in at 140,000 pounds of 140,000 pounds of payload capability, 69 metric tons. SLS Block 1 will take 57,000 pounds to the moon. BFR, SpaceX, they're looking to take 220,000 pounds to the moon, but that's not direct. They can get you 220 to LEO, but you're going to have to do on-orbit refueling to be able to get that back to over to TLI, to get it over the translunar injection, to be able to get it to the moon. So there's a lot of aspects going on back and forth. There's a lot of different makeups of rockets, but they all have different capabilities. They all serve different needs. So the idea of, well, why are you doing this or why are they doing that? It's because everybody has different values and different purposes and different capabilities. It pretty much takes everybody to do our space exploration that we want to do. Everybody's growing. You can't just jump right into it. And so as people create their capabilities, as they step on the shoulders of the giants moving forward, as SpaceX grows, New Glenn grows, Virgin Orbit comes into play, Mass in Space comes into play, they have suppliers. There's a whole multitude of companies that are being developed and working together. ULA is building their new rocket. They're partnering with Blue Origin for engine supply. They're working with Aerojet Rocketdyne for their second stage engine supply. It is not a single company organization any longer. Just like for the NASA as an agency, it's not a single agency effort any longer as well. Not even for anything that we want to do. It's all going to be about our partnerships and our ability to work together to create the capabilities that we need and to leverage off of that and go off and do the space exploration we want. So any of you that were just listening and listened to Kevin O'Connell talk just there in the latter part, he's right. It's a $1 trillion industry that's growing, and it's going to grow into it. And it takes a lot. It takes technology. It also takes government participation. It takes getting licensing out of the way. It takes making it easier for companies to get their launch capabilities in place. There's going to be a lot of work and a lot of effort that's going to be done to give us the opportunity and the ability to do what we need to do what we want to do, as well as to create the marketplace and monetize what can be done in space. So as industry comes along and technology comes along together, it's the entrepreneurs, it's the technology developers, and that's what's making it happen for us. And so that's what we're looking for within NASA and within Marshall Space Flight Center and the other NASA centers that you'll be hearing from later today as well. It's all about getting our partnerships to be able to make it happen. We're a government agency. We're here to help you. You've already paid for us with your tax dollars, might as well take advantage of it. So, whether you're doing Stardust Space Center, whether you're doing Ames Research Center, whether you're doing Kennedy Space Center, whether you're doing Yolanda Johnson Space Center, we're all here to understand what your needs are, because we have capabilities that we're willing to share with you and that we want to share with you. We want to make you successful. We want to make things happen for the space companies that are developing and the space companies that are already established. So from rockets, that'll get us to low Earth orbit. That'll get us to the moon. It'll even get us to Mars. But what about beyond that? So there's a lot of opportunities that we have for that. And so that's where Marshall is exploring the use of solar sails. So that's where it goes, rockets and sails. So sails are a pretty kind of neat thing. There's been a lot of work that's been done with them, a lot of technology development, and that's exactly where it's still at. There's very few flights that have actually happened. Iconos with JAXA back in 2010, they flew their sail up into going to the sun for sun studies. It was 196 meters square, and that was about it. Trying to develop the technology. How do you deploy them? How do you steer them? How do you work with them? There's all those capabilities that come from it. The interesting part with it is, if you've got a solar sail that's 800 by 800 meters, and you're 1 AU, so you're right here around Earth, distance away from the sun, it'll generate 1.1 pounds force of thrust. Not much. Even more interesting is the acceleration that you're going to get from the Earth's, the solar winds and whatnot. You're looking at 1 millimeter per second squared. That's not even a rat fart. I mean, we are talking, that is nothing, man, for acceleration. But with that continual growth, and you're not carrying any fuel, you're just using the solar winds, and you keep going, and keep going, and keep going, and keep going. With the solar sail, you can probably get to Jupiter, not probably, you can mathematically. You can get to Jupiter in 2 years, and when you get to Jupiter, you're going 17 kilometers per second. So that's 38,000 miles per hour with 1 millimeter per second acceleration, per second squared. So the capability is immense for what you can do and where you can go. Granted, you're maybe not taking too large of a payload right now, but you'll be able to get out there pretty quick. So Voyager 1 launched in 1977. Anybody know what year it passed the heliosphere, got out of our solar system? Anybody want to guess 2012? Great guess, 2012. So 35 years later, it took us to get from Earth to the edge of the solar system with Voyager 1. If you're to use an inflatable beryllium sail, which the beryllium would also have an interaction with the solar winds, and now it's kind of taken off, it gets some greater acceleration from it, you can get to the heliosphere for what took Voyager 1 35 years, you'll get there in 2.5 years with the solar sail. That's frickin' cooking. So now interstellar transportation is possible. There's a company, Pete Warden's involved with them out of the Ames Research Center. He recently was a center director there. Breakthrough Stardust is the company. So they've got $100 million in financing already. They're looking to develop and break down the technology barriers that they have. But their goal is to send 1,000 chipsats with solar sails. They want to power them with a power beam laser from Earth. They give them a 10-second shot to give them 1,000 G thrust or acceleration into it. They figure that they can get to Proxima Centauri, the planet orbiting Alpha Centauri, in about 20 to 30 years. That's 4.37 light years away. So the capability, the opportunity for getting into interstellar space, for getting to our nearest star, it's not out of the realm of a single person's career span of 20 to 30 years. So that is pretty freaking phenomenal. What do you do with that? I don't know, but I'm looking for some entrepreneurs to figure it out. What could we do with that? What kind of, where are the opportunities there? Whether you're going to Alpha Centauri, Proxima Centauri, or whether you're just going to the outer planets, whether you're going beyond that, is there a monetary value to that? Can you monetize that technology? I don't know, but this is something that we're looking to explore. In my mind, NASA's always been there to pave the road, to set the foundation, to get the infrastructure in place so that other companies can come in and benefit from that, take advantage of that, create a marketplace economy that they can benefit from, the nation can benefit from, and we're making sure that we can have that foundation established for them. So through rockets, through solar cells, we want to make that a possibility for any space company to take advantage of, for any young entrepreneur to take advantage of. Obviously, there's lots of challenges with the solar cells, cell material, you got deep space environment degradation, you've got deployment limitations, you got communications, how are you going to communicate from distances that far? So all of those are being done with near-term technology developments. So the Science Mission Directorate realizes that, they see benefit in that, and so they're putting out calls. They have a call now for science missions that are focused solely on technology development. In fact, if you focus your proposal on the science and you have greater science PIs than you have technology development PIs, your proposal will be marked down. So they are taking a serious look and a serious interest in improving technology that they can benefit from for doing science, not only here on Earth, but in interstellar travel as well. So we're very excited about that opportunity. There's quite a few sails again. Icarus flew out in 2010. NanoSail D from Marshall Space Flight Center flew out in 2011 with a 10 meter square. Light Sail 1 and 2 by the Planetary Society, so outside of NASA. They're doing solar sails as well at 32 meters per meter squared. We have NeoScout, which hopefully is going to launch in 2020, with a joint venture between Marshall and Jet Propulsion Laboratory with an 86 meter square solar sail. And then Marshall is talking with other partners as well for potential proposals to put in to do a solar sail mission with have a 700 meter square sail, developing purely the technology of being able to deploy a sail of that magnitude and try to get it to work. So there's opportunities abound for new technology, old technology rockets, as well as the exploration of where we came from. So the Stardust part of rocket sails and Stardust. So Marshall is one of the few centers. We have work in heliophysics, astrophysics, planetary science, and earth science. So all 4 fields that fall within the Science Mission Directorate at NASA headquarters. Within our heliophysics, we've been flying a mission and operating a mission called Keynote. It's a partnership between JAXA and Marshall Space Flight Center. So it's been focused on space weather and solar flares and sun observations and making a better understanding of how that interaction is occurring. If you really want to see some very cool videography of what's going on with our sun, do a search for NASA Hinode, Hinode. The website that we have there, phenomenal. So I was taking a look at it a couple days ago and just seeing some of the latest stuff that we have published up there. It's pretty awesome. We have 3 instruments on board the Hinode spacecraft, the Solar Optical Telescope for the magnetic field observations of the sun. We also have an X-ray telescope and a UV imaging spectrometer. So we're just trying to get a better understanding of what's going on. Why is that important? Obviously, solar flares and the emission of solar gases is a big significant issue to us for ComSats, as well as disruption in comm systems. And so we want to make sure that we have a better understanding. When we see an activity, what's the effect of it? Can we start doing better predictions? Can we become better weather people to be able to predict space weather and how that would affect our satellites that are operating in geosynchronous orbit, as well as our satellites that are operating in LEO. On the astrophysics side, we do a lot of work. We've had Chandra flying since July of 1999, an X-ray orbiter, an X-ray telescope flying. So it's kind of interesting. Chandra orbits at about 86,500 miles above Earth, mostly to get out of the Earth's atmospheric region that would affect X-rays. So our Earth's atmosphere will absorb up X-rays. So they want to make sure they get beyond that to be able to get a good, clean view of what's coming from space and do those analysis and gather that data to do that exploration of what's going on there. The telescope itself is pretty phenomenal. It can resolve a stop sign at 12 miles, which I thought was pretty awesome. It also, more impressively, runs on 2 kilowatts. So that's pretty much equivalent to a hairdryer that you get in your hotel room. So pretty minimal power usage, pretty maximum capabilities for what we're trying to do there. Again, studying the X-ray emissions coming out of exploding stars, coming out of galaxy clusters, as well as studying the matter around black holes. IXPI is a project that we recently were awarded at Marshall, and we're looking to develop that and grow that capability, be able to have a launch here in 2021. It'll be orbiting about 330 miles above Earth. The Imaging X-ray Polarimetry Explorer, again, to study cosmic rays polarization. And so what that's going to is understanding, again, the magnetic fields of black holes, neutron stars, pulsars, and other anomalies out in space, and other aspects out in space Again, trying to figure out how are things formed, how are they developed, how did they grow, how did they create, what happens to them when they die, how do they implode, how do they explode, all the aspects of the formation of the universe, and trying to have a better understanding of that. Again, going back to digging that hole in the sand, we're just trying to understand what's going on out there. On Earth Sciences, we have what we call Little O Sport, because we also have a Big O Sport. So Little O Sport is a short-term prediction research and transition center. This one I think you're going to love. It's focused on Earth observations, Earth gathering data, because what they are doing is providing that information to organizations and centers to be able to come up with better weather predictions at a regional level. Wouldn't you love it to listen to the weather report and it's actually right? That'd be awesome. So trying to get that data, trying to get it to the right people, trying to make that happen, trying to make it right so when you put your jacket on in the morning because the weather person said so, that it was right. And then it's freaking cold outside and that's why you're wearing your jacket instead of getting out there and going, holy cow, I'm way overdressed. So we also have Severe, which is a really neat joint venture with NASA and USAID. And what they've done is we're taking all the geospatial satellite data that we're collecting through NASA and sharing it through hubs across the world. We have partnerships with NASA, Goddard Space Flight Center, JPL, Ames, Langley, Environmental Protection Agency, NOAA, National Weather Service, USGS, the US Forest Service. The geospatial data that we're gathering is pretty phenomenal in the Earth observation aspects. So we're getting surface water mapping, vegetation mapping, surface temperature mapping, any aspects that you can be able to observe of what is changing on the surface of the Earth, gather that data, and you can provide it to anybody, especially when it comes to severe weather disasters, natural disasters themselves. So you have flooding in Myanmar, when you have droughts in sub-Saharan Africa. How is that drought happening? Where is it happening? People understand it easily at a regional level. You can see what's around you. How do you understand it at a more lateral, larger level when you take a space-based observation and you get real-time data showing what has happened over the last 5 years and how there's been a transition or a migration of water, a collapse of vegetation, or a growth in whatever temperature deltas around the region? Now you begin to understand what's happening at a larger scale. What's affecting it? Is it a dam was built? What did that do over here? How did that affect the vegetation? You can start to see those transitions and those relationships to see what the effect is to develop solutions to solve those problems. And so that whole project and program, Severe, has been highly successful on a global level to help make the world a better place and a better place to live in, to grow in, and to grow and survive in. And so we're making sure that we're trying to make life better for anybody here on Earth. Lastly, we have sport, our Big O Sport. So scintillation, the twinkling of stars. So we all see that phenomena. For those of you who are stargazers, and you go out and you look. Well, that same scintillation occurs not only just for the viewable, visible light spectrum, but it occurs in other spectrums as well. So when you get it into the radio wave spectrum, now you have scintillation in radio waves that are being transmitted. So okay, what does that mean? Well, that means that your ComSats and your GPS aren't as accurate or as correct as they could be, or they should be. Understanding scintillation better, being able to correct for it, improves that accuracy that you have, and that's exactly what Big O Sport is highly focused on. So the scintillation prediction observation research task is out there to try to better understand the equatorial plasma bubbles in the ionosphere, as well as the interplanetary scintillation. They're gathering that information, they want to gather that data and be able to go figure out how can we improve satellite communications, and how can we improve GPS, as well as how can you predict when you're going to have poor, degraded systems, and so you can take advantage of those opportunities as well. So we focus on so heavily at NASA, and many companies are focused on this, we want to provide opportunities for our youth. High school, college. We want to help them, motivate them, inspire them, create our workforce for the future. That's all grand and that's all great, and that works. What we're trying to do, and I'll say this collectively for all the NASA centers and the other folks that manage partnership offices, through partnerships, we want to do the exact same thing for companies, small and large, entrepreneur startups, well-established. We're here to help you, to stimulate you, to create opportunities. We want to inspire you to delve into greater levels of space exploration so that you can leverage off of what our capabilities are, and then we can leverage off of what capabilities you develop. We want to grow companies so that we can use you later on to help satisfy the needs and help meet the requirements that NASA's establishing, Congress is establishing, the President is establishing through the space policy for what we want to do for space exploration. That's what partnerships are about. It's about partnering with companies to create opportunities for them to grow, to create opportunities for them to monetize and become more financially stable. But we want to make sure that you have opportunities to work with NASA to make those opportunities available for yourself to create greater economy within the space environment, within the space business. And that's what we're focused on, and that's what I hope you'll have the opportunity to engage with a lot of the NASA centers that are here, the partnership managers, looking around. See Yolanda? So we have Yolanda Marshall in the back from JSC. We have Tom from Kennedy Space Center. We have Rose from Ames Research Center. Harvey, from Langley, from Glenn Research Center. So we have a lot of folks around here that you can engage and talk with. A lot of them will be talking here later on today as well. But I hope that you guys have a great SpaceCom, and I hope you have the ability to reach out and connect with some folks and take advantage of what you have here and grow your space companies and help us make this a cool endeavor that we can grow into. Thank you very much.